SwayamPrabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on turbulent premixed flame, and we have looked at the fundamentals like turbulent split, displacement split and all this. Now we are discussing the BML model, and we have seen the turbulent scalar flux closure, and now we are looking at the source term. So this is how the source term one can close it. So I mean the source term can be represented like in local mass conservation and in terms of flame surface density, and once you write in terms of flame surface density, either one can use algebraic model like this, which is quite simple, or transport equation like this, where the transport equation of the flame surface density contains convective term, local change, turbulent transport, then production due to stretch or flame stretch or annihilation. So now there is one thing, there is no chemical time scale involved. So the turbulent time, which is tau kappa by epsilon, is the determining time scale. So as we can see here, epsilon by k comes into the production of that. So there is a limit of infinitely fast chemistry. Now using the transport equation, we can model for chemical source term, which is independent of SL. So that's what we can find it out. So that means when you use this source term closure, either use the simple algebraic expression, or you can use the transport equation to close it. So that's how we talk about the BML model. Now we move to the level set approach or G equation approach. Now here you have an instantaneous flame front. This is our instantaneous flame front, and there are so many points where you can show the kinematics of the flame front. The kinematics of the flame front can be examined by examining the movement of single flame front particles. So these movements, which are influenced by local flow velocity, which is ui 1, 2, 3, and then burning velocity. So this movement of these particles, they are essentially, so in one instantaneous flame front you can assume to have so many particles, and using that you can basically the kinematics, the kinematics means essentially in this is called level set approach. That means you try to capture these propagating flame front. So by capturing the flame front, you want to model this particular way. So, once we say that the local velocity and all this will lead to the kinematic equation of the flame front except by dt equals to ui plus SL Ni, which is our nothing but the normal vector. So, then we can have the same flame front where G less than 0 and G greater than 0. So, this could be our burned side, this could be unburned side, and this is G of xit is 0. So, another way to one can look at, instead of observing a lot of particles, one can examine a scalar field like G. So, the isosurface is defined like G of xit is G naught is 0. So, that is the definition of the isosurface. Now, we can find out the total derivative of G. This is on the flame front. So, which we can write dg by dt del j by del t plus d xfi by dt into del j by del xi, which is 0. So, this is what you get, the total derivative of the G on the flame front. So, now once we look at the kinematic equation, so that will now, this is our instantaneous flame front, which is G xit 0, this is our burned side, this is unburned side, and this is the normal. So, the normal vector can be calculated del G by xi modulus j, and now the kinematics of that individual particle can be written at ui plus SL Ni and del G by del t plus this would be 0. So, which using these two, it leads to del G by del t ui del G by del xl equal to SL delta G, where delta G is the square root of del J by del I del J by del I. So, this is an famous or well known G equation for premixed combustion, where you track the flame front and of this turbulent propagating flame. So, now for this flame front, like where this is G less than 0, G greater than 0, and this is G xit 0, you say del t by del xi xl del G. So, this is our local change, this is the convective change, and this is the progress of flame front by burning velocity. So, there is, one can see no diffusion term involved there, and this particular equation is applicable for thin flames and well defined burning velocity. and also it can be applied to corrugated flamelets, where your flame is L delta and which is eta is that. So, this particular zone also you can use it. Now, if you look at that flame front, this is my equation from the G surface del xi. So, kinematics, now kinematic equation is no more a function of density. So, this is valid for flame position, where G equals to G naught equals to 0. Now, to solve this, G needs to be defined everywhere. G needs to be defined everywhere in the flow field. So, there are different possibilities which are available to define G. For example, one is the very common, that is used signed distance function, which use delta G equals to 1. Now, we see the other thing, like what is the influence of chemistry by SL. Now, SL is not necessarily constant, but it is influenced by strain, curvature, which is kappa, and Lewis number. So, then one can write down this modified burning velocity using this impact. So, modified burning velocity is written as SL equals to SL naught minus SL naught L kappa minus LS, where this is influence of curvature, this is influence of strain. So, now the kappa is defined as where del Ni by del Xi, which is del Xi of G by Xi by magnitude of G. So, if you look at this, which is G0 and G less than 0, this is a position where one needs to do this position kappa 0. This is curvature where kappa is high, because kappa is defined del Xi minus del G by del Xi by mod G. So, our SL, there are two terms, SL naught L kappa, LS. This is how the kappa is modeled, and these two terms one can think about, these are uncorrelated laminar burning velocity. So, one can think in that way. Now, the other terms which you have, SL equals to SL naught minus SL naught L kappa, LS. This L, which is known as mark strain length. So that L can be determined by experiment, or by asymptotic analysis. So the correlation which one can use is that LU by LF, this ratio is 1 by gamma, LA 1 by 1 minus gamma plus JD LE minus 1 minus gamma by 2 gamma into 0 to gamma by 1 minus gamma ln 1 plus xi by xi dxi. So this guy is nothing but density ratio, and this is Geldov's number, which is JD is E by R TB and TB minus TU by TB. It is Lewis number, which is lambda by rho Cp d. It's a ratio of Smith number by Prandtl number. So these are the different terms which contain there. So now using this, so we got SL equals to SL naught minus SL naught L kappa S. So these two terms are uncorrelated. These are Mach strain length, this is curvature, and S, which is strain, which is defined as minus Ni del Ui by del Xj Nj. Now using this expression, the extended G equation one can write, which will looks like del J G by del T plus Xi equals to SL naught L kappa Ls delta G. So this is what your extended, because we use an expression of modified burning velocity. So this is slowly, if you see, we start with a simple expression for SL, then we incorporate the effect of curvature and strain and all these, and then slowly, so that goes to the more like an realistic situation where due to turbulence you will have all this effect. Now we go to, now we look at corrugated flame rate or thin reaction zone. Now, so the previous examination which was limited to corrugated flame rates. So that means in the corrugated flame rates you have thin flame structure, structures which is eta greater than LA L delta, and laminar burning velocity well defined, right. So what we get the resume of thin reaction zone, which is like where your small scale eddies penetrate the preheating zone. You will have transient flow and burning velocity is also not well defined. So that means these things are no longer valid. So the problem that one encounter, does that means this level set approach is valid in the thin reaction zone regime? So that is a bigger question to now answer. So what happens, we can see if we go to thin reaction zone regime. So this is ignition point, reaction zone, preheat zone, that's a typical. So here the G0 can be surface which is represented by inner reaction zone. If we do that, in the inner reaction zone, what we have, so the which is thin compared to small scale eddies, that means my L delta will be smaller than eddy, so that we can describe our temperature as T naught. So our temperature equation will take the shape of rho ui xi rho d plus Wt. Now one can look at the isosurface of temperature, which is T xit is T naught. Then we can write dt by dt, which is T naught, where dt by dt plus xi dxi by dt at T naught, which is 0. So which essentially is sort of an, one can think about the similarity like del j by del t, del j by del x by xf dt 0. So it's a similar kind of expression, one can look at it like what we obtained earlier. Now we write the equation of motion. So the equation of motion for T naught xfi dt ui naught plus ni sd, which was a similar expression which is written for level set approach, equals to ui plus sl ni. Here we bring in the displacement speed. Now this displacement speed, which is defined as del del xi rho d del t by del xi plus Wt rho del t, t equals to T naught. Now similarly you can find out the normal vector. So, that is defined as Ni equals to minus del T by del Xi divided by del T at T equals to T naught. So, which is an similarity, one can see that Ni equals to minus del J by del Xi by del J. So, this is how we define it for that thing. So, now we can use this G naught equals to our T naught, we write that del G by del T Uy del Xi equals to del Xi rho d Txi plus Wt rho delta T, which is a T naught delta G, and this guy is nothing but our displacement speed. Now, the diffusion term, which is the normal diffusion and curvature term, will be invoked. So, we will have diffusion term, which is normal diffusion, that is Sn, and curvature term, which is order of kappa. So, there we get rho d equals to Nj del of Xj rho d Ni by del T by del Xi minus rho d del T Xi. So, this is nothing but my kappa, and this is the term which is nothing but my normal diffusion. Now, if I put everything together and write down the equation for this, so the G equation for this thin reaction zone, we get del G by del T plus Uy del G by del Xi Sn plus Sr minus d kappa into delta G. This in a collectively you can think about SLS, then this one can write del J by del T plus Uy del G by del Xi SLS delta G d kappa delta G. So, that is the equation you get, where Sr is Wt divided by rho delta T. So, this is what you get for the G equation in the thin reaction zone. Now, we will stop here today and we will see how we can come up with one G equation which can be applied to both the regime. We will continue the discussion in the next lecture.